it's 260 is out now. And he's the #1. And he scored almost double or second place. So the food is good, the speaker is good. So guys, give some props to
thank you, Is this working?
Yep.
Yeah. All right. I'm not known for being the loudest voice, so it's important for this to work. Thank you very much for coming, and thanks Vivian for the very generous introduction. So it sounds, I'm sorry to say this, but it sounds much more impressive than it actually is. So I worked. Let me show this to my. This is me. So I want to tell you a little bit background. So I used to work at the insurance industry. So I worked several years in Travelers, and I worked 2 years at AIG before I got a Boston-based startup called the Data Robot, which builds multi-platform. So one thing that I learned from my corporate career is that it's very important to manage expectation. So we did do a very good job today. So I'm trying right now. So I'm going to give about 1 hour of talk. So to cover a few topics, basically my personal take on how to do well in Kaggle competitions. And if you have any we have relatively a large crowd, so that if you have any questions, please wait until the end. We have about half an hour of open Q&A session, so everybody will get a chance to ask questions.
Yes, guys, you can please #OpenTalk, and we will capture your question.
All right. So today I'm going to cover these few topics. So first I will give a quick introduction for how data science competition is structured, at least how Kaggle does it. And I want to cover a few pointers on how I do it. So there's a philosophy, strategy, and also techniques. And then I will have 2 example competitions, so 2 that I did relatively well. I just want to use that example to show what I actually do, and also I want to show that every competition is quite different. So those are actually quite 2 very different competitions. So the last I want to cover, what's the things that we learn from a competition, are they useful in the real world or not? I do want to answer that question at the end because I get asked that question quite often. So how data science competition is structured. So this is at least how supervised learning competition is structured. So usually we have the host of the competition will have all the data, the predictors and the target. And then they will split the data into 3 pieces. So there's the training piece, which we can all download, and we have both the predictors and the target. And then there is the public leaderboard piece, where we have training for all 3 pieces. The difference is what we know about the target. So we know all the target exactly for training. We get a summary metric on the target for the public leaderboard. So after you build a model on the training data, then you apply the model on the public leaderboard data, make predictions. And then you can upload the predictions. They will give you, because the host, they have the server, they have all the target variable actuals in there, they can actually compute your prediction. They compare your prediction with the actuals to see how well your prediction predicted. They will tell you with a summary score. And that's where the public leaderboard is. So throughout the competition, usually lasts a few months, you will get a constant feedback of how your model performs on that piece of data compared to all the others. So you can get some sort of idea for, if you're doing the right thing or not. But at the end of the competition, what really determines the outcome of this contest is actually the private leaderboard ranking, which you only get to see once. That's after the deadline passes. Then they will switch over from the public to the private. It depends on the competition. Sometimes the public leaderboard and the private leaderboard actually are, it's more often than not that they are very similar. So you'll see some changes in ranking, but actually there are a few competitions that public leaderboard and private leaderboard are very different. So there is quite a bit of uncertainty involved. So why the competition is structured that way? Because this forces us to do what the predictive model is supposed to do. That is to predict things that we haven't seen before. So the private leaderboard matters most because we have absolutely no knowledge about the target variable on the private leaderboard data. So, and that is how our model will be used in the real world. So whenever we build whenever we build a supervised learning model, the purpose is to use the model to predict something that we haven't known yet. So if we know something already, there's no reason to predict it. You can just look at it. So it's very important that to evaluate the model on data that the model does not have knowledge of, at least on the target. So a little bit philosophy. Actually, I'm quite fond of philosophy because when it comes to predict something that you have actually no knowledge of, there's really nothing to go by a lot of times, so you have to fall back on philosophy. So, I'm sure that most of you have a certain data science background, so that we all know that one of the biggest pitfall in building models is overfitting. So overfitting basically means that you have a data set, you have the training data set, and you build a model on the training data set, and you can, throw a lot of parameters at it, try all kinds of different things. You can build a model that fits the training data set very well. However, the model may or may not generalize. So you can have a model that does exceptionally well on the training data set, to predict something you know. But if you build a model that predicts very well things that you already know, but it does not do well on things that you don't, then that will be a model that's overfitting. So in this case, in a lot of Kaggle competition, the overfitting actually is the kind of biggest risk. So here, what I learned through the years is that there are many ways to overfit. So there are many ways to overfit. So so the easiest way to overfit, I think we all know that, is to have too many parameters in your model. So if you have 100 data points in your data set, and you have 1 million predictors in there, you can probably predict it exactly because you have so many different freedom. But that's only the most common way of overfit. There are actually many other ways. So one very subtle way of overfitting, let me call this. One very subtle way of overfitting is that you keep building different models, and you test each model against the answer, which is usually the public leaderboard. And then you see whichever model works well, you keep it. And whenever it doesn't work well, then you can drop it. You can keep doing this. Actually, in a lot of situations, you can keep doing this, and you will find that your model's performance on the public leaderboard just keeps growing, keeps improving. There's almost no end to it. But the reality is that you are just overfitting the public leaderboard. So I think that happens quite often. It's like in statistics. Okay, I'm not a statistician, I mean no offense to statistician in the audience. But in statistics, we always use 5% the significant significant test, so that if something is giving you now hypothesis, if you have less than 5% chance of observing what you have observed, then you would say that okay, this is significant. But we run into multiple comparison fallacy very often in building models, especially when you try very hard. You randomly try 100 things, then a few of them will turn out to be significant, statistically speaking. But that's because you try many things. So here the philosophy is that think more and try less. So the next one is the data secret. So this is the secret slide. So some people ask me what's the secret of doing well in Kaggle competition. This is not the secret. So there are a longer version on the left and a shorter version on the right. So okay, the slides will be posted somewhere, like either on Vivian's website or in SlideShare. So there's no need to take notes on the slide content. So the short version is that why you need to be disciplined. So the temptation to overfit the public leaderboard is actually very strong. Sometimes psychologically I cannot control myself, but just to overfit the public leaderboard because that makes me feel good. Okay, we are human. I mean, but we need to be disciplined and remind ourselves that we don't want to look a little bit embarrassed after the private leaderboard comes out, right? So if you do so well on the public leaderboard, then it flips and they say, you couldn't find yourself anymore. It doesn't look good. So the next is to work hard. Kaggle, at least Kaggle's system rewards effort. You never lose anything by participating. So you can rank the absolute last on a contest, then you still, relatively speaking, do better than not participating. So usually participating more get you better results. And even within a competition, as long as you are disciplined, trying to work hard is always helpful. And we will touch on that on how to properly work hard later. The next one is learn from everyone. This also is a little bit against the human nature. So we all have our own pride, right? So occasionally I would think, okay, this time I will just try to do everything myself. So I don't want to look at what other people do it. And there's a little bit like hubris in there. But on the other hand, that people other than you always know better than you individually, right? So because there are so many of them and only one you, right? So it's pretty hard to compete against everybody. So I always feel that it's really learning from others that you can really improve. And there's really no pride in like doing something by yourself. Otherwise, actually I'm not sure how many people can really invent all the mathematics that you learned in elementary school. And I think that takes more than one lifetime to invent all that. So there's really no such something like, oh, I learned this myself. The next one is luck. So we are predicting, a lot of times that we are predicting very noisy data and on things that we haven't seen yet. And there's really no, there's no absolute differentiator between noise and signal. There's not. So the only way to really differentiate them is that you have more data, which for data science computation, there's none. You have that much data, there's a signal noise ratio that's pretty determined. So there's always non-zero luck. So if you participate in something and you don't do very well in a particular computation, so that's probably just bad luck. But if you do well, that's all your effort. That's how I see it. So I always get reminded before I go to give a presentation. I always get reminded, make sure that I bring something concrete. People can take away, right? So the rest of the presentation is something that is more concrete. But I personally really feel that is how you approach the problem. It's actually the philosophy and the strategy is actually more important than specific techniques. So that I don't want to say that, oh, just learn all the techniques, then you will do well. Actually, let me go back to the previous slide. So a lot of times that it's not about which one you do, right? So there are a lot of specific things that is necessary to do well, to build a good model. It does not need to be a competition. Even in reality, you want to build a good model, you probably need all these as well. The key there is actually how to allocate your effort. We all have a time budget. There's a deadline, and then we have to do our day job and feed our kids and keep our kids. So there's only a limited number of hours per day. So it's actually worth it to think about how much time you want to allocate into doing feature engineering, how much time you want to allocate into trying different form models, and how much you want to allocate to doing hyperparameter tuning. So I do think about that consciously. Now, back to our technical tricks. So this is concrete stuff. So gradient boosting machines. I use GBM on everything that I can use GBM on. There are things that you can't GBM. So one example would be very large data. If you have 100 million observations, you probably don't want to run GBM. But for anything that I can GBM, I probably overuse GBM. why GBM is so good, and I think by now probably most people already know GBM already, but let me cover that anyways in case. So GBM will automatically captures to a very large degree nonlinear transformations and subtle and deep interactions in your features. So, GBM also gracefully traces missing values. So I use the R implementation of GBM. This is package GBM very often. There are actually at least four very good GBM implementations today. Actually, that's like 2 years ago there was only the R one that was good. But nowadays you can use either the R package, you can use the sklearn package or GBM. That's also very good. And if you want to go parallel, you can use either the H2O's version or you can use XGBoost. They are all very good implementations, and each has their own kind of quirk. But they all are able to do nonlinear transformation interactions. So these are actually, those two things actually are what people spend most of their time on when we are building linear models or generalized linear models. So in the days when we only had like a logistic regression or when we had only Poisson regression in the industry in insurance like we work. So we spend actually, whenever we're building models, we are not really building models because we always run the Poisson or gamma regression. So it's always the same model. So what we are doing is look at all the outliers, all the transformations, either the U-shaped, like W-shaped, or whatever shaped, hockey stick shaped. Or we try to do this interaction, that interaction. If you use GBM, all the things are taken care of for you automatically. That's why I use it so much. So if you haven't tried, please do try. So GBM, like everything, like all the other like modern machine learning algorithms, it has a few tuning parameters, and when your data data size is small, you can just do grid search. But actually GBM has actually 3 separate, pretty orthogonal tuning parameters. If you want to do grid search, you actually do need a pretty big grid. So I usually use some rule of thumb kind of tuning, so it's mostly for saving time. So if you do a very smart grid search, you can probably do better than the rule of thumb. But rule of thumb is, very time saving. So the first set of tuning parameter is how many trees you want to build, and the learning rate. They are reciprocal to each other. So higher learning rate will get you to use less number of trees. I won't save time, right? So usually I just target 500 or 1,000 trees and tune the learning rate. Start from 0.1 and then we'll go up down a little bit. The next one is just a common tuning parameter for the decision trees. So GBM is based on decision trees, so it needs the decision tree parameters. The number of observations in the leaf node. So usually that I just look at data, you can get a feel for how many observations that you need to get a good mean estimate. So if your data is very noisy, then you may need more. If your data is pretty stable, you probably need less. So just use that number. Actually, I feel that's actually usually turn out to be pretty good. And then interaction depth. This interaction depth is a very interesting thing for the R version of the GBM. The R version of the GBM interaction depth basically describes how many split it does. So it's not interaction depth as in the tree depth. If you have interaction depth of 11, so that means you have 10 leaf nodes, actually about 10 leaf nodes. It doesn't mean that you have 1,000 leaf nodes. So don't be afraid to use 10. I use 10 very often. So there's one thing that the GBM that doesn't do. Actually, there's one thing that all the tree-based algorithms do not do well, which is dealing with high cardinality categorical features. So if you have a feature that has, which is a categorical variable, that has many levels, throwing them into anything tree-based is a bad idea because tree will either run super slowly if you want hot encoding all of them, or explode or just overuse that feature because it's overfitted. So for high cardinality features, you have to use them in the tree. You have to somehow encode them as numerical features. There are a few different ways of encoding. So I just want to mention that actually high cardinality features are very often. We often see them like zip code, or if you do medical data, you see a diagnosis code. There are tens of thousands of CD9s. Or text features. They are all very high cardinality features. So one approach of encoding them is actually build you can build a regression. You can build a range regression. Just do a, especially in a logistic case, it's very simple. Add L2 penalty to your logistic regression based on your categorical features. And then you can then use that prediction itself. That would be a numerical as an input to your GBM. I will cover more detail for a particular example for how I do this. So it's actually a pretty standard idea. So that's what usually people call stacking. So basically you build like a stack of different models. And the subsequent stage of models will use the previous stage models as output as their input. So as I described, if you have text features, you have numerical features. You get all the text features into your rich regression model. And then you will make a prediction. And then you put that prediction side by side with all your raw numerical features, and then feed this into a GBM. And this usually works pretty well. And if you haven't tried, then if you can replace this by like a categorical features. You can do that too. And for a lot of Kaggle competitions, you just do this. You rank like a top 25% at least. So for people who rank at the bottom half of Kaggle usually don't use GBM. That's what I think. Because it's actually quite easy to rank like a top half. There are many like beginners or people who like really get into this on the bottom half actually. So the one particular risk here is that if you use the same data to do this, you use the same data to build the first stage model, and use the same data again on the GBM model, on the model 2. Very often, the prediction 1 will be overfitting in your model 2. Because the prediction 1 is you already used the target variable once, building prediction 1. So whenever prediction 1 has the leakage in there. So basically, it has leaked the information from an actual target. So whenever you put a prediction 1 like that together with numerical features, the prediction 1 will be given too much weight. And the more you overfit the model 1, the more weight it will be given to prediction 1. So actually, it can be quite bad. So what you want to do here is that you already want to use different data for model 1 and the model 2. So you already want to use different data. So you can split your data in half, use half data for model 1 and half data model 2. And that usually gives you a better model than using all the data for model 1, all data for model 2. And you can swap them. You can split your data into half is A, half is B. Use A to build the model 1 and then build model 2 on B, and then use B to build model 1 and build another model 1 and model 2 on A. You have to do that, so you can use all the data that way. Then that seriously gives very good results usually. And if you are not trying to win a competition, right? So for practical purposes, actually I feel that kind of model is already good enough for a lot of practical applications. So okay, here. So also you can take this one step further. If you have a smaller data, then even doing half maybe limiting your data too much, you can actually do something like cross-validation. You can split your data into 10 folds and do 10 different model ones. Each one using 9 predicted the other one. Then you can then concatenate all the models together so that each record will have an out-of-sample prediction from model 1. Then you can avoid overfitting problem in the model. So that's how you deal with the categorical features. Once you can basically code them and then put them into GBM. We are still using GBM. The next one is that the GBM's the feature engineering is just a greedy space search, so that it can't really find very specific transformations. So, for example, a lot of times when we build like a sales forecasting model, so the best sales forecaster is actually the previous time period sales. So if you want GBM to automatically discover that, I think actually that's pretty difficult. So if you know that, definitely. So that covers the GBM. The second most often used tool by me is actually the linear models, like generalized linear models or regularized generalized linear models. I used to use GlibNet very often. That is, it's also very popular R package. So from a methodology perspective, GlibNet is actually all the generalized linear models are kind of opposite of GBM. So all the generalized linear models are global models, assuming everything is linear. And all the tree models are local models, and assuming everything is a staircase shape. So they complement each other very well. The linear models become quite important when your data is very, very small, or when your data is very, very big. So for different reasons. So when your data is very, very small, you just don't have enough signal to support non-linear relationships or interactions. It's not that there isn't. There always is non-linear relationships and interactions. But if you don't have enough data to detect them, it's better to stick with the simpler one. So that's when the linear model works well. On the other end of the spectrum, when you really have billions and billions of observations, only linear models are fast enough for you. So everything else will never finish in our lifetime. So that's why you're going back to linear model when data are very large. So the linear models, when you do a model blend, I will cover model blend a little bit later. So when you average, basically you blend the models together, GBM and GlibNet complement each other very well, so you get a very nice boost in performance. The downside of GlibNet or anything similar to this kind of model is that it requires a lot of work. So that all the things that GBM does for us automatically, I have to do that myself. I have to deal with all the missing values, all the outliers, all the transformations and interactions. It really takes a lot of time. And the last thing I want to cover is the regularization. This is my personal, how do I say that, bias, is this. In this day and age, if you are building linear models without any regularization, then you must be really special. That's really a thing, right? So it's seriously. So if you are building a linear model without regularization, that you must be working somewhere really special. So always regularize. So it's required. So there are two very popular regularization approach. One is L1, one is L2. So basically L1 gives you sparse models. L2 just make everything's parameter a little bit smaller. The sparsity assumption is a very good assumption. So actually the book called The Elements of Statistical Learning, that's a very good book. It actually discusses why that is the case. So the reason is almost like a Pascal's wager. I don't know how many people know that, but the point is, if your problem is sparse in nature, assuming sparsity will get you much better model than not assuming it. If your problem is not sparse in nature, then assuming it wouldn't hurt much. So the lesson is always assume sparsity. Always assume, unless there's other exceptions to the rule. Unless there is a problem you know is not sparse. So there are actually problem that we know is not sparse. So things like text mining, or if you are doing some sort of like zip code. If you build a zip code based model, then if you think what is sparse in the sense of a geographical distribution, that means like there are 3 zip codes that are special. They have some kind of parameters, and everything else is the same. So that's the same thing like in text mining. If you assume that 500 words in the English language is very special, and then all the other like 100,000 is not useful. That's not possible. So in that case, when you're doing text mining or doing very high cardinality categoricals, that's where you do not assume sparsity. But other than that, it's pretty safe to assume it's sparse. So let's go to text mining a little bit. So first, I admit that I'm not a very good text miner, if that's a word. I just, I read, I Google things and I read whatever other people write, and then I try to follow their examples. My approach to text mining is the simpler stuff usually works better. As far as we have come on the machine learning, the n-gram-based approaches, n-gram and naive based approaches actually work surprisingly well. And a lot of times actually it's quite hard to do better. So here on text mining is always, my view is make sure you get the basics. The advanced stuff is less likely to work. The basics such as n-grams, and also the trivial features such as how long the text is, how many words in the text, and if there is any punctuation stuff. Those kind of features are actually very important. And the last one is a lot of problems that are heavy on text are not necessarily driven by text. So this year's KDD Cup actually is an interesting example. So the KDD Cup is a problem. It's actually sponsored by a New York-based company. They have a website. That website where you can donate to your local school's teachers' projects. So if you're a teacher in elementary school or high school, you can post a project saying, I'm doing this reading club with my students. I need $100 to buy this carpet. People really post those. And then if you find, if you sympathize with that effort, you will say, I give you $100. You can give 10. People can add together. So they call it donor choose, so that as a donor you can choose which project is sponsored. So they set up the competition to see which project is more likely to get attention from people and more likely to be funding. So the teachers will put up essays and summaries of their projects. So it's a very nicely written essay. Some people write very nice essays, not everybody. So that all the text data are provided, also together with the cost and type of project. And so that, there are not so many texts, right? If you look at the data, whenever you have unstructured data, the text always is way bigger than the structured data. So that I always feel that I am obligated to use the text a lot. But it turned out that essentially some other features are much more important. So for example, projects that cost less are much more likely to be funded. So that doesn't need the essay to tell you. If you ask people for $1,000 for a laptop, no essay will save you. So it's much easier to ask for people for math books. So that's how the data tells us. That's right or wrong, I don't know. So next one is blending. So if you if you do one computation on Kaggle, then you will learn this. So it's almost never that a single model will win a competition. People always build a variety of models and blend them. Blending is just a fancy word for weighted average of models. You can do a little bit fancier than weighted average, but not that much. I usually just use weighted average. So my rationalization for why blending works is that because all our models are wrong. So as George Box said, that all models are wrong, some are useful. And there are lots of good sayings in statistics. So I like this one very much. All models are wrong, but some are useful. I would like to think that all models are wrong, but mine are useful. There's also another one that I would like to mention, which is this. I think I forgot who said that. It's very hard to make predictions, especially about the future. I forgot who said that. This sounds very good. Yeah. So that's right. So like when we study regression analysis or something similar in school, we always start our models with the IID Gaussian assumption, like independently identically distributed Gaussian errors, right? So in my entire life, I've never seen a real data set with that distribution. Let's put that way, okay? It never happened. I don't know where it should happen, but it never happened. So our assumptions are never right. So whatever you assume, unless you're doing a simulated data set, unless that is always wrong. So the hope of that is that our models are wrong in different ways, so that when you average them, their wrongness kind of cancel each other out. That's how I justify why it works. There are a few things to keep in mind. One is that simpler is usually better when things are uncertain. So if you are not sure, just add model 1, model 2, model 3 divided by 3. That's usually better than tweaking the parameters, unless you have a lot of data. The next one is that there is a useful strategy which is intentionally overfit the public leaderboard, and if you do it carefully, actually it may give you a nice boost. So what you do is this: you build many different models and you submit them to the public leaderboard individually, and then you, based on their score, you keep the better ones, and then average them, and that's your blend. So this actually, at least on public leaderboard, that will give you a nice boost. This model definitely work better than any individual model you submitted. So either that will work better on the private leaderboard or not, depends on how much data you have on the public leaderboard. So if you have a lot of data on public leaderboard, actually this helps you, because when you are doing this, you are actually implicitly using the public leaderboard data as your training data. So you actually have an advantage over people who don't do this, a real advantage, if the public leaderboard data is large enough. But if it's not large enough, you're just overfitting public leaderboard. You will do terribly bad when that thing comes out on private. So it's totally based on data volume. One thing that's very useful in building blending is actually you are not going after the strongest individual model. You want a model that always you want a model that work, but you want a model that different. Sometimes actually intentionally build weak models help a lot when you add them to a strong model. So the key is diversity. I'm sure HR people will be very happy to hear this. We need diversity in model building. So that's true. This is actually scientifically proven it's good. So there are many ways of building diverse models. So here's a few examples. There are the infinite ways doing that. So you can use different tools. You can use different model structures. You can use different subsets of features. You can use different subsample of observations. You can build models that are for weighted problem. You can build both weighted and unweighted models. Usually the unweighted one would work worse than the weighted one if you have a weighted problem. But if you can take 90% of a weighted model and 10% of the unweighted, it will work better than the 1% weighted. It's quite often. But here is try to build those models more or less blindly. Don't look at the answer. The public leaderboard is just hanging there and you always want to test them. Try not to use that as a guide to filter out your models, unless you are confident that the data set is large enough so that you can actually use that way. So it's a total judgment call based on the noisiness and size of data. Before I go to the real examples, I hope I have one. Okay, I have an example. Let me try to address this question objectively, although it's not possible because everybody's fast. So sometimes people ask me that certainly I enjoy, you can tell I enjoy doing competitions, right? So other than being a fun game, is there anything really useful for competitions? So first of all, let's acknowledge that it's a fun game, right? So fun game itself is entertaining, so that's real usefulness. So we shouldn't dismiss fun game as something not useful. But beyond that, there are two ways of looking at this. So the modeling competition only covers actually a very small portion of the necessary work to make data science really useful in this world. So in order to make that, to make a model really useful, we need at least another 3 pieces. So one is that we need to select the right problem to solve. So if you find a problem that's interesting only in abstract way, but there's no real-world implication, there's actually no immediate value. The next one is that we need to have good data. So the model certainly is a garbage in, garbage out problem. So if you don't have good data, you cannot expect to have good models. The third one is that we need to make sure that models are used the right way. So a lot of times that it's possible to build very good models, but then they are implemented wrong. It can be trivially wrong. It happened to me in the past that we build a pricing model in insurance, and then you implement, they swap the parameters in the model. It's like x1's parameter goes to x2, and then you figure, oh, this doesn't work. Then you say, oh, they swapped it. I really don't ask why they swapped it, but they do. So with all these 3, plus the right generalizable model, then you will have right solution. So building the model, the fun part of building the model like Kaggle is only a small portion. We all need to keep that in mind in reality. But that said, computation helps us in many different ways. So I have 2 ways that help the sponsor. So if you have a company, either a startup company or enterprise, doing a modern computation for your own data set is very helpful. So 2 ways that helps you is one is help you measure to a degree the signal versus noise in your data. So if you put up a reasonable price money, then you can be quite sure that 99% of all the signal that you can squeeze out of your data will be squeezed out by the people on Kaggle. Kaggle people are quite good at that. And the second one is if there's any flaws in your data. So a lot of times because of the data collection process issues, you may have predictors that are not real predictors, such as if a particular field is missing, you always have a yes or no as an answer. So if you have anything like that, the Kaggle crowd will find it for you, and you can go back and fix it. The model is not useful if you have that problem, but at least you can fix your data. But as a participant, so I learned 2 things, among others, 2 major things from Kaggle. One is that I have to build generalizable models. Just predicting what I know is useless. That discipline actually is hard to learn discipline. The next one is to fully realize day to day, every day basically, that there are other approaches, there are other people with better ideas. So it's always keep me on my toes and keep me learning new things. Otherwise, it's quite easy to just hide in my corner and think, oh, I do really good modeling work. So. And then I go there and I try to say, oh, I'm an idiot. It happens quite often. So let me just give 2 examples of 2 computations that I did okay well. So one is the Amazon user access computation. So this is one of the most popular computations. It used to be the most popular, but recently the Higgs computation had more participants. So this one has about 1,700 teams participating. I got 2nd place on this one. This actually is one of the interesting experiences for me, because I was number 1 on the public leaderboard, and I didn't try to overfit the public leaderboard. Sometimes I do, so this time I didn't try, and then I still lost somehow to another team. Never figure out why. So the problem is to use anonymized features to predict if an employee access request will be granted or denied. If you work in a fairly large company, this is very often, right? So I need to access that folder, then somebody might say yes or no. And all the features are categorical. So they are basically like resource IDs, manager IDs, user IDs, department IDs, and then 1, 2, 3 for all numbers. And then many features have many levels. But I want to use GBM, right? So this is where I convert all the categorical features into numerical. So there are 2 ways that I use to encode the categorical feature into numerical. One is like how many times that level appears in the data set. And you can do this for all your categorical features and all the interactions for categorical features. And then another one is use the average response. So basically average Y for that level as a predictor. So here you have to do something slightly more complex than doing a straight average, because straight average will lead to overfitting on thin levels. I will show you an example on the next page. And then beyond those encodings, the final model is a linear combination of 3 different kinds of trees, plus the glibnet, and plus 2 subset features based trees. So this is a blend that at the end I tuned manually. At that time, I did not fully understand the online learners like Wopa, Wabbit. So I didn't use it. So in retrospect, if I use those kind of things, I think I will get a better model because they have a very different algorithm. So this particular competition has a requirement that everybody has to publish their code, so that my code is up there on the GitHub. Okay, do not evaluate my software engineering skills when you read the code. So here is this is something that is very easy to do actually for encoding categorical features by doing the average response. So the data set is this is very simple data set. So we have one categorical feature that it's a user ID, and it's for the level A1 we have 6 observations. 4 of them is in the training data, and 2 of them is in a test data. So for the training data, you have the response variable that's 0, 1, 1, 0, and the test data you wouldn't have the response variable. So here shows how to encode them how to encode this into a category, into a numerical. So what you do is to calculate for the training data the average response for everything but that observation. So for the first one is 0. For this particular observation, there are 3 other observations in the same level. That's number 2, 3, 4. And it's 2 out of 3, that's why it's 0.667. The second one, it also has 3 other observations, but it's 1, 0, 0, so it's 0.333. Do not use itself. If you use itself, then you will be overfitting thin data. Sometimes it also helps that to add a random noise onto your training set data. It helps you smooth over very frequently occurring values. For example, if you look at this, you will see that 0.667 and 0.67, 2.67 and 2.333. Actually, when you throw those kind of things into GBM, actually GBM go nuts because it treats them as special, almost special values. So if you add a small noise on top of that, it actually makes a little more real from data perspective. You do not need any such special treatment for the testing data. Testing data is a straight average of the response value for that level for the training. So 2 out of 4, that's 0.5. So this is all you need to do to use categorical features in GBM. This is actually much easier to do compared to build a separate ridge regression. And I do this very, very well. So that's Amazon. So Amazon computation is a very simple data set. Mostly just do feature engineering on anonymized categorical features. And the response is 1, 0. So the all-state computation is unique in a different way that it has very structured target variables. So it has 7 correlated targets. So it's called A, B, C, D, E, F, G, which represent the options people choose when people buy personal auto insurance policies from Allstate. So you can choose like you want a comprehensive coverage, you want a 100,000 limit on VI or PD or whatever. So this turned out to be a very difficult computation for 2 reasons. Actually, a lot of people hate this computation a lot. So one is that the evaluation criteria is all or nothing. So you have to predict all 7 correctly to get a point. If you predict anything wrong, that's 0. So basically, partial answers got no credit for this one. People hate that a lot. We had a long debate on the Kaggle forum, but the Kaggle people didn't watch. So next, I heard the story was even Allstate was upset with them. So even the sponsor wasn't happy. So the next one is the baseline model. There is a trivial solution to this model, which is very good, which is the problem is to predict the final purchase option based on earlier transactions. But whichever option they choose for their last known transaction is actually a very good predictor of the final purchase option. So the model is like, if you just use the trivial last quoted as the predictor, no change. It's right about 53.269%. You really need a lot of decimals to see the difference. That's why the decimals. And then I got the third place in the competition. So I predict I'm able to improve that by 0.444%. And then the number one solution improve another 0.03%. So we did. This is I'm proud to say that this is statistically significantly better. I don't know if it's a business significantly better or not. That I don't know, but it's statistically speaking significant. The challenge to this is actually most on the target developer side. So the A, B, C, D, E, F, G are not independent of each other. Actually, every one of them can be predicted very well, more than 90% accurate. But when you put them together, they have actually quite interesting structures. And then the two challenges that capture the correlation and not lose to the baseline. So I built chained models for the dependency. So I first build a freestanding F model. And then assume you know F, you build a G model. Then assume you build, you know F and G, and then you build the next, and next you build one other. And you can actually change the order for models to put your free models first and dependent models later to make the model better. Actually, this works quite well. And this is, in my way that it's a little bit more theoretically appealing because it's actually one systematic model. There's no like hand tuning in like, oh, I want to put this combination, that combination. So the next one is, in order not to lose the baseline, basically we build two-stage models. You build one model to decide either you want to use the baseline or you want to use your prediction. And then when you want to use your prediction, then you use a prediction. Otherwise, stick with baseline. So at least for the for the dummy cases that you do as well as the baseline, and for where you can find improvement, you improve up. So I think that's how you can improve upon a very strong baseline. So to finish, there are a few kind of trivially useful pointers. So one thing that I highly recommend is that to participate, if you want to learn how to build generalized models, really participate in the competition. Just watching it doesn't count. So so from my own perspective is that it's the more frustrated I am doing it, the more I learn after. So it's like I couldn't solve this, other people do so well, I really hate myself. But then I look at other people's answer and say, oh, that's how they did it. You really get a very good learning experience that way. If you're just observing it as a spectator, I really don't get into the problem. And really read the forums, so people really post very useful notes, and that's the very good. They also post like links to papers, to books. And next one is, okay, I need to admit that I have no PhD. So my education was in engineering. It's related, but it was neither in statistics nor in computer science. So I learned a lot just basically reading books and reading Kaggle forums. So one book that's very good is the Elements of Statistical Learning from the Stanford guys. So highly recommend it. That's like the Bible of machine learning, but in a way that. So if it's also freely available, legitimately, on the internet. Okay, a lot of things are freely available on the internet. It's legitimately freely available, so please take a look. It covers really these very good survey book for all the statistical learning approaches. The next one are the pretty simple ones, such as the scikit-learn package in Python, cron, and then things like Wobit. Wobit actually is quite useful. I've been using that a lot recently. So with that, and hopefully I didn't hold it too long. Thank you.
So we can take 5 questions. Has to be good one. Otherwise you're banned from this group, okay?
All right. Okay.
I have 2.
Oh, that's.
But the first one's super quick.
One.
Okay, so my second question is, what's your take on using neural networks in competition for tasks that aren't don't screen neural networks like image or audio recognition.
If you are doing image recognition, please use a convolutional neural network.
Yeah.
Otherwise, you're dead. Don't even try anything else. Yes, I think even for other computations, you can use neural network. But I think neural network has the advantage, has the disadvantage. Other than the CNNs, in the general problems is that neural network has been out of fashion for a while. So there aren't a lot of very good packages to build like regular neural networks outside of the convolutional stuff. I think that's why it's not as common. Sir? Question? No?
I have a question.
Okay, all right.
So in the private data board, when they give the test data, right?
Yeah.
If they have some fields with the data like NA or something, when you develop the model, you will eliminate those things. But is there a situation where the data set given doesn't contain any of those things, but the actual data will contain it? So do we need to think through all those situations and mitigate those things, or how does it work?
What kind of things? Do you mean on the feature side or on the target side?
So what is the smaller training data set they provide?
Yeah.
Assuming that contains no NA value, so we create a model for that
Oh.
without mitigating those factors. But what if the original data contains those things? So do we need to think through all those things while developing?
Yes, you do. So because you are always given the predictors
Right.
for the private leaderboard, so you can tell if there are NAs or not. So if there are no NAs, there's nothing to worry about.
So they won't. So which means as long as the original full data set contains an NA, then in the training set also they will provide those things.
Not necessarily. You can have a field that which has absolutely no NAs in the training, and then there are NAs in the
So which
private.
means for every field I may need to mitigate or do that
No,
translation there?
you are provided the private leaderboard data, so you can tell if there are NAs. If there are NAs, you have to treat them. But if there isn't, you don't need to worry about it. So you don't need to guess in that way.
But what if my model will not work in the original data which contains NA? Because I worked on a model from the private data which contains only without NAs.
You are given all the data on the predictor side, so there's no uncertainty in that way.
Okay.
We can cover this later in more detail if I can.
Alright.
Okay. Question?
Yeah. In my experience, you went through a couple different things. One is the choice of different models and
Yeah.
blending models, and
Yeah.
the other is kind of feature engineering
Yeah.
and all that. In my experience, it's the feature engineering that gets you more the distance toward the goal. Better models can get you the last little distance. But like especially in business applications, where you have to win a Kaggle competition, you know, there's very fine differences, between, as you were saying, between the top people. In business, the difference between GVM versus trees versus lasso ridge, whatever, for me is less is less important than getting one hot encoding, like different predictors, and kind of making sure that you're running your analysis on the right variables. But what's your opinion?
That's almost like it's almost like a food and water, which one is more important for survival, right? So it's both necessary. So I want to agree with you that I think that in a lot of cases that the feature engineering is certainly very important, especially if you know that there are good feature engineering for that particular problem. But I think in a lot of situations that the line between model and feature engineering is not really that clear. So that in the case of GVM, it actually does interaction for you. So that makes it much less necessary for you to identify the interactions. So it's basically it's actually quite likely that for predictive problems, GVM with no feature engineering will actually beat the logistic regression with feature engineering. It's by a reasonable margin. So that's basically that's how I feel about it. I think it's problem specific. Okay, that's not the answer.
Do you have any thoughts on like for online learning, whether you use linear models or using some like Bayesian techniques?
I have no idea about online Bayesian techniques actually, so I can't comment on that. So I use a lot of the follow the regression leader kind of online learner stuff. Those are very good.
Hi.
Too many. Okay, all right.
A lot of times we have the requirement of using the same model to both predict and as well as explain the driving factors. Like, and sometimes they will not be the right things because the predictors might not make business sense. And I don't know, a lot of times we are in this situation where we
don't know whether to go ahead with the model or not.
Yeah.
So how do you suggest addressing that need with the teams or anybody you're working with?
Oh, okay, so first, on Kaggle, we have the luxury of not needing to explain anything. Okay, so that's one thing that's a good thing. In reality, that it's actually it's actually quite common to build models to have one prediction model, but another separate, different, simpler interpretation model.
Okay.
Actually, if that is at all possible, I think that might be a reasonable approach. Beyond that, that really depends on what your model's purpose is. There are two kinds of models, actually. So to think about predictive, supervised predictive model, there are two kinds of models. One is you only need to predicted outcome. In that case, one example would be like pricing in insurance. So you just need to know predicted outcome, who is more likely to have accident. In that case, complex model is very acceptable. But there's another kind of model which is more, it's kind of like interventional model. Based on whatever your model says that you want to do something different. So in that case, you are actually leaving the predictive modeling and into the causality study. In that case, it's strongly preferred to use simpler models and avoid at all costs of complex interactions, because there's no way to differentiate. Actually, it's very difficult to differentiate correlation and causality in observational data only. So simplified model is much better in that way. So it depends on the purpose. How many questions do we have?
One question.
Girl first? Any more girls?
You mentioned GPMs and GLMs. How about time series? What kind of models do you recommend for time series data?
Oh. There are two ways of doing time series. So one is the proper time series way, which is all linear models. All the proper time series packages are linear models fundamentally. And the other way is to convert a time series problem into a non-time series problem and GBM it.
Cool. I think we have to wrap up here. If you have more questions, welcome to chat with Owen
Yeah, we can
in
chat
person.
individually.
Yes. I found the same thing. Want to teach how to do city bike prediction. How to predict how many bike and dogs will be there in 5, 10, 15 minutes.
Okay.
The last 5 minutes actually give you the best prediction. I use GPM, I use time series,
course.
I use all kind of
that's the
techniques.
It's very hard to beat the baseline problem.
Yeah. Okay, guys, we have a traditional way to evaluate tonight's speaker's performance. We're gonna vote for him. So this means he's awesome. This means he's super awesome. This means you don't want to see him again. So let's see. Owen, can you turn around so you only look at me?
All right.
Can you be out here?
Okay.
Okay, guys, we're voting. Honest, okay? Okay, I will show you later. Awesome. Wow, you have all the hands in the ear.
All right, thank you. We have a request from our host of this location that if you have any plates or cans or things, please take them and put them in the trash can, because they have, as Anna said, there is a very early session tomorrow, so whatever we can do to help them clean up, highly appreciate it.
Thank you.